Okay. So anyway, so I was studying uric acid, and that took me to, we had this evidence that it was driving blood pressure and might have a cause in hypertension. And we did this study actually in adolescents who are overweight, where we lowered uric acid in them and their blood pressure corrected it. And we published it in the JAMA. It was, a big deal.
And that was done through medical intervention?
Yeah. We used the drug to lower the uric acid, and 90% of them or so became normotensive.
Wow.
It was amazing.
And by the way,
they never received a blood pressure pill.
And that's your area of expertise,
right?
That's your background as a kidney doctor.
That's right.
That's really your bread and butter of what you studied in your career.
So then the question was, what drives the uric acid up? And, most people think of alcohol and actually things like red meats, but actually one of the major things that raises uric acid is fructose and sugar. And so actually Gary Taubes, who I'm sure interviewed me related to a paper that was published in the New England Journal on gout and its relationship with diet. And when we were talking on the phone, he says, well, what do you think about sugar as a driver of uric acid? And I said, well, it definitely is a driver. It's the fructose component. And then, after I had my conversation with him, I went home and I thought, we should give fructose to animals and see if they develop high blood pressure. And if we lower the uric acid, can we lower the blood pressure? Because at this point I was focused on blood pressure. And so what happened was, some people in my lab, Taka Nakagawa, we gave fructose to animals and they became hypertensive. And so fructose is that component of sugar. So table sugar or sucrose is half fructose and half glucose. And there's another sweetener, high fructose corn syrup. It's also about half and half fructose and glucose. But fructose is the only sugar that raises uric acid. And so we gave fructose to animals and they became hypertensive.
Their blood pressure was high.
Yeah, the blood pressure went up just like this. And we gave the drug to lower the uric acid and the blood pressure came down. But there was a big surprise because the animals that got fructose also started getting fat and they started developing insulin resistance. And their fats went up in their blood, the fat went up in their liver. I mean, they were developing obesity and metabolic syndrome right in front of us. And when we lowered the uric acid, we actually could reduce all of those. And I go, oh, it can't be. It can't be just lowering the blood pressure but also lowering all these other things. And then we started realizing that fructose was, first off, it was a very potent driver of obesity. But the other thing is we could lessen it by lowering uric acid. And the cool part is uric acid's not in the caloric pathway, so there's calories, everyone says it's calories, but
calories are calories are the big driver of obesity.
Right. But uric acid was being produced independently of the calories. And when we block that part, we actually were blocking, the obesity. And then we said, well, what's driving it? And we started doing 1 million studies. And what we realized is that fructose actually makes animals obese by affecting their appetite. Basically, it induces, it blocks the ability to feel full. And so animals will keep eating, a lot. I mean, they eventually stop eating, but they eat a lot more than they're supposed to. And it turns out that they become resistant to a hormone called leptin. And when they become leptin resistant, they'll eat and eat. Now, if you give them just fructose, they don't gain that much weight because the fructose is only 4 calories per gram. High, fat is 9 calories per gram. So if you make them so they're hungry, and then you give them that fatty food, then they get fat.
Access to other sources of concentrated calories.
Right. Then they get super fat. So the fat, we could show that the fat was really important for the weight gain. But if you just gave the animal fat, they didn't gain as much weight. It was much, much less.
They ate the food. They felt the signal of leptin, which said, I'm full.
Yeah.
Or I'm not as hungry. And so they didn't overeat, but if they had fructose, they couldn't sense that signal leptin. And so they kept on eating if they, in particular, had access to highly concentrated calories in the form of fat.
Yeah. And we even did an experiment where we gave fructose to make them leptin resistant. And then we stopped the fructose and they stay leptin resistant for several weeks, like 2 or 3 weeks. And then if you put them on a high fat diet, they gain a lot more weight with a high fat diet than they would with just a regular high fat diet. So the leptin resistance could carry over. So if you stop the sugar and you think that you're good, for at least a couple of weeks, you can stay leptin resistant.
Got it. So there's a little bit of time that it took.
Yeah, before it went away.
Both for animals, but probably as you're theorizing for human beings too, that if you are used to and your body's used to eating a lot of fructose, we'll talk about the top sources of fructose in a second in our modern diet, then you could end up in a place and position where even if you pull back from those foods, you still have the urge to overeat.
Right. And then what we did is we studied this. We found that the way fructose works is it's unique from all other calories, from all other foods. It's the only food that drops the ATP in the cell. And the way it works is how you can say, well, how does if you're giving fructose, the calories should increase the ATP, you would say. Except remember, there's two sources of energy. There's two energies. There's the ATP, which is the active energy, and then there's the stored energy. Together, they equal the total energy. So when you eat calories, you try to keep your ATP levels high. You want the gas tank full. You don't want the ATP level to fall. If it does, it's like an alarm signal, gas tank,
running on empty.
Close to empty. So normally we try to keep our ATP full. And then if there's extra energy, it goes into the fat. The fat is kind of the backup. It's like the luggage, but you want the gas tank full. What fructose does is it lowers the ATP level by acting on the mitochondria. It stuns the mitochondria so they don't make as much ATP.
It's almost like a little bit of poison for the mitochondria.
It does. It's oxidative stress to the mitochondria. And it's very specific and it knocks out different aspects of it. And the result is that there's less ATP in the cell. And instead, the energy gets shunted to the fat. Energy balance is maintained. If you're eating energy, calories are a type of energy. You will either burn it or store it, and it gets stored here. But you keep the ATP levels low. So what happens is the body thinks it's starving. It's so because it feels like there's not enough energy. So you keep eating. And then eventually the ATP levels recover. When you have a soft drink, there's this period of time where the ATP level falls. You can measure it by using special NMR and things like that. You can actually measure the ATP like in your liver after drinking a soft drink, and it plummets.
A traditional soft drink, one of the big brands that is sweetened with high fructose corn syrup.
High fructose corn syrup for sugar. And so it's the fructose that does it. So when we started studying this, we go, oh my gosh, obesity is also a low energy state. If you biopsy the liver or the muscle, the ATP levels are low. And if you biopsy, in diabetes, if you look at the tissues, the ATP levels are low. All these are low energy states, and yet everybody's eating more.
Right. They're having so many calories. So you're thinking, why is this person?
Their total energy is high because it's all stored.
It's all being stored, and something's signaling to the body, don't use this energy, but actually store this energy. And that goes back to this idea of uric acid and fructose being a poison to the mitochondria.
Yes. And so it turns out that, a lot of people were thinking of obesity as you cap off the tank and the extra goes into fat. But actually the trick is to drop the ATP to make you eat more and to shunt the energy to fat. So let's just go through this again. So like the energy balance, people say that it's mainly fat is the main thing that's driving weight gain. And, you know, if
because
you do, because it's the highest density of calories.
Right.
And if you're going to do a short-term study and you do carb restriction or fat restriction, you might actually lose more weight by doing fat restriction. And the low carb people say, wait a second, if you go on a low carb diet, you don't even have to, you know, you don't even have to restrict calories. You're going to lose weight.
Right.
And it's just, and the both are right.
They're both right.
And it turns, and I've submitted a paper, it's under review, that unites all these different hypotheses, because this work that I'm talking about actually does unite these pathways. So for example, if you go on a low carb diet, after a couple of weeks, you're going to become leptin sensitive. And so you're going to really control, you know, you're going to, you're not going to be gaining weight despite being on a high fat diet. So a low carb diet's often high fat, yet you're not gaining weight. This doesn't match with the energy balance people who say, well, if you go on a high fat diet, you should really gain weight because it's got the most calories.
And one clarification about that. Sometimes the energy balance folks say, well, you're still eating less calories. And then the people on the other side say there's two different camps. There's one camp that says, well, calories don't matter. You can even be eating a lot more calories and not gain as much weight. And then there's the other side that says, well, you just don't crave as much calories, right? So you're not, because you're more likely to connect in because you're leptin sensitive. You're like, okay, I got it. My brain got it. I'm full. I don't need to eat anymore.
That's the key. So you become leptin sensitive when you go on a low carb diet. So you're going to fill up much quicker. And if you're leptin resistant, you're going to keep eating a lot. But what drives calories, you know, is really, it's the fatty foods have a lot more calories. So it's really easy to gain weight if you are leptin resistant, you know, with fatty foods. So
especially in our world of ultra processed foods, where you have the perfect combination of often, you know, high carb, high fat, sugar, salty, it's all the things together. It makes it super easy for people to gain weight.
So what we did is we gave fructose, and we could make animals obese. They developed all features of metabolic syndrome, you know, insulin resistance and all these things. And we realized it was a survival system for them, because they're thinking that, you know, that they're in a low energy state. So storing fat will help them. You know, it's like what the bear does before it hibernates. It will eat all this huge amounts of fruit, which has fructose, to help increase their fat stores so that they can make it through winter. They become insulin resistant so that the blood levels of glucose are high, so that those areas of the brain that are not insulin sensitive can get fuel, preferentially over the muscle, where the muscle, insulin resistance in the muscle reduces the glucose uptake in the muscle. So when you're insulin resistant, what happens is the muscle becomes resistant to the effects of insulin in particular, and they use less glucose. So the glucose levels go up in the brain, and there's more glucose for the brain. So it actually, you know, if you're starving, you want your brain to get the fuel more than anywhere else. So insulin resistance can be a benefit to the brain acutely, because it removes the glucose from going into the muscle to be provided for the brain, for those areas of the brain that don't require insulin.